are very difficult to know. So and what hopefully I have been able to develop through these lectures is the idea that it's much more productive to think of these systems as, or to think of the emergent collective behavior of these collections, large collections of particles, as being dictated by the constraints that they have to satisfy. So don't focus on precisely what's going on at the microscopic scale. Let's just say we know for certain that these constraints have to be satisfied. And if all of these particles at every scale, right, have to satisfy these constraints, then what are the possible, what kind of stat mech or what kind of collective behavior does that lead to? So reminder from yesterday, right? So for the for the spin problem of frustrated antiferromagnets, the Ising antiferromagnet, we ended up defining a field which is like an electric field in the sense that the divergence of E is zero, is the statement of constraint satisfaction. And from that, then we said there are two sort of winding numbers that one can define, Ex and Ey, stemming just from that. So I can then group my states according to the values of these electric fluxes, and all microstates within a sector specified by these two winding numbers can be explored through local rearrangements. Okay, so that's one concept that we will extend to the granular systems, the existence of a Gauss's law of this kind. And I also briefly, and that's mainly will be the focus of the coarse grained continuum theory that I'll talk about today. But we also discussed the fact that in this frustrated spin systems, there is a gauge potential, which we call the height, which can be introduced, right? So we just bring that up, mind you. Right, so just a reminder from yesterday that we introduce these heights, which is a way of mapping the dimer configuration into a height configuration. So instead of specifying the dimers, I can now tell you what are the heights at the centers of these hexagons, and that's a microstate. And again, coarse graining either coming from this divergence idea or from this height idea and maximization of entropy ideas, we came up with the Lagrangian, which in terms of heights, I can write in this form or this form, right? So I'm now going to explore these concepts, how or if these concepts can be translated into the granular problem, right? So I'll first talk about this sort of the analogs of these winding numbers, and then I'll talk about heights, and then I'll come back to this Gauss's law idea and the emergence of a gauge theory, right? So when I say emergence of a gauge theory, what I'm saying is the constraints in the spin problem gave us a Gauss's law, and that's the basis of saying the coarse-grained long length scale behavior of these lattice spin systems can be described by a kind of electromagnetism, not a kind of electromagnetism, and emergent electromagnetism, which satisfies all of known Maxwell's equations. So this is a picture that's that I'm trying to illustrate, that I'm using to illustrate the idea of these winding numbers in the granular system. And I have drawn a picture in 2D, but and I will talk explicitly in 2D, but the concepts are, as you'll see, translate up to 3D. So instead of thinking of our classical spin systems, now think in terms of this granular packing on the left-hand side. And let's imagine periodic boundary conditions. This is on a torus, so this is the torus on the right-hand side. Again, I can use the fact that, okay, so let me backtrack a bit. So these granular assemblies that I'm drawing on this left-hand side all satisfy for every grain, right? So every grain satisfies these two constraints. So if I sum over the contacts around that grain, FC has to add up to 0. And the torques have to add up to 0. So keep this in mind. We will use this to define the analog of the heights in a coarse-grained sense. And keep this. I'll keep saying coarse-grained. I think one question that anyone should, not anyone, one question that should bother people is what length scales do we need to coarse-grain over to get these properties? And I'll try to address that at the end, but hopefully, this is a question that'll arise in your heads. So translated into a continuum problem, what we are saying is the divergence of the stress tensor is 0, where the stress tensor, or the stress tensor by definition is 1 over area sum over all contacts. Let me get backtrack. So I'm thinking of this now as a coarse-grained field, right? So sigma is a tensor. I'm going to try and use the double arrow so that we don't get confused with a hat for a unit vector. So this is a tensor that exists as a function of space. So it's a coarse-grained field. And the way I'm going to define it is to say, or I'll actually use, I interchangeably use these two notations. So this, remember, is the extensive version of the stress or the force moment tensor. Oh, and Abhishek, you asked me, I think yesterday or day before, the connection of the definition of this stress tensor with the things on the boundary, right? The way we normally define it. So just a comment, if you want to look up the way I'm defining it, this would be called the virial stress. This is the way people compute it in molecular dynamics, simulations, etc. Not by creating a boundary and measuring the stress, the forces there and the normals, but actually computing it this way. So I'm going to mostly be using this, the force moment tensor, which is the extensive quantity, and this is the problem. So this is the summation symbol, and this is sigma. This is the sum over all contacts inside some box, right, situated at R. And this outer product. So I'm taking this box, right? And I'm looking at all contacts that appear in here. For each contact, if I know, and I don't necessarily know the forces and the position. This is the coarse grain quantity, let's say, that one can measure, but I can define it by taking the tensor product of the contact vectors and the force vectors on every contact and summing them up. So then I will, for this box, if this is the center of the box, I can define a tensor sigma located at this point, which is a sum over all of the contacts in that area. In practice, we will take small boxes and define it. And that coarse graining length scale, which I will refer to as delta, is a question of what's an appropriate coarse graining length scale. And that is actually an interesting question, which I
so Bulbul, I mean, so what you're saying is this definition is the same as what one would have in a molecular.
This is actually the way you
can
compute it in molecular
Right.
dynamic simulations,
Right,
because you know the interactions, you know the positions, and this is the
Right,
way
yeah.
to compute it.
Okay.
So this is referred to as the virial stress because the trace of this is the virial.
Right, yeah.
The virial pressure is, if I just
Right.
take the trace of this, the RIFI, the R dot F, that's the virial, that's the internal virial.
Right.
But yes, it's completely equivalent to the other definition.
Right, yeah. But in a fluid, of course, I would do some averaging, but
Exactly.
like time later. But here, it's just a fixed thing. Or
So,
you're now
in
going to
in a fluid, I would do a time average or a
Right, yeah.
configuration average.
And so,
As you
yeah.
will see, we have to do a disorder average here also.
Okay.
Otherwise, it doesn't. This gauge theory doesn't emerge.
Okay.
If you look at a single configuration, like, of course, you can take a single configuration and take a large one and look at individual.
Right, yeah.
But that question of the coarse graining length scale and if this kind of self-averaging actually exists or not is interesting. And at the unjamming point, and this is where I that's why I introduced this isostatic coordination number or contact number at exactly the point where z is equal to z iso. You will see that I have to average over the whole system to even define this scale. So define this coarse grained quantities. So then, of course, self-averaging fails completely. So I have to take this length scale over which I have to coarse grain for this gauge theory to be well defined actually diverges at the isostatic point. So but those are subtleties. But yes, I have to do disorder averaging. Okay, so let's imagine that yeah, so I can define this for each configuration, but then when I compute correlation functions, etc., from the gauge theory that will emerge, I have to do disorder averaging. so I can't just stick to one network. The difference here is in the contrast with the spin systems is there's no well-defined ladders, right? So I have to add, so the underlying network is fluctuating from place to place or different configurations. But yeah, let's explore those at these questions at the end. I think that's in the things that we are still trying to figure out. So if I define this quantity, then I can show explicitly that the divergence of this is zero. I can actually do this at every grain and keep coarse graining up to. So this definition doesn't suffer from the coarse graining length scale. This definition is fine. The divergence of the stress tensor is zero. Is okay. It's some other aspects that. So the divergence of the stress tensor is zero. And so that's the coarse graining of this. So the coarse graining of this gives me the divergence of this force moment tensor or stress tensor to be zero. The coarse graining of the torque equation tells me that except at the boundaries in the bulk, sigma ij has to be equal to sigma ji. So it's a symmetric tensor. Okay, so this is also what in fluids we say that the stress tensor has to be symmetric if there are no internal torques coming from polar. And you'll see that friction creates this interesting, that there can be a torque density, but it gets pushed out to the boundary. So well, that will be, that we can see clearly from the gauge theory. So divergence of the stress tensor is zero, and sigma ij equal to sigma ji is the coarse-grained version of our force and torque balance equations. So because this is zero, right? Remember, this is a tensor. I can, just like we did for the vector E field, now I have a tensor, right? So again, I'm going to connect. So this is the analog of the divergence of E equal to zero in the spin system. So I'll wherever I'm connecting to the spins, I'll try to consistently use this color green, right? So now, just like we had for the spin system, I can define now two vector quantities in two dimensions. I can define a vector fx, which is a loop, let's say, running along the x direction on my torus. So I have periodic boundary conditions. So this is now sigma dot the unit vector that's perpendicular to this surface, right? So it's n, the normal to the x direction, which is y, right? So I'm calling, so this is my x loop, this is my y loop, and so this is nx, which is along the y direction, this is ny, which is along the x direction. So it's a little bit, I don't know which one is easier to use, but so this is now a vector, right? So what I have is, so okay, let's do this explicitly in 2D. So the tensor sigma is sigma xx, sigma xy, sigma yx, sigma yy, and we are going to use the fact that sigma xy is equal to sigma yx, right? So then the fx is the analog of one of the winding numbers from the spin systems, is going to be sigma xx, sigma yx, Sorry, I did this wrong again. Okay, I know I'm doing, so I'll pause after writing this to see if there are questions. So I'm dotting it with nx, which is along the y direction. So what I have here, and then I'm integrating along x from minus L over 2 to L over 2. Similarly, I can define a fy. Right? So what I'm saying is this is a straightforward generalization of what we saw in the spin system. We said there are two winding numbers, ex and ey, which now go over in 2D to two vectors that are the analog of these winding numbers. And it's the reason that these are sort of, again, topological invariants is that the divergence of the stress tensor is 0. So if I take any closed loop, then of course this winding this has to be 0 because I'm integrating over the divergence of the stress, and these two loops, and that's the point of this sort of schematic picture here, is that I can draw these loops any way I want to. It doesn't depend on how I draw it, again, because of the locality of these force and torque balance constraints. Just like in the spin problem, we said that the number of dimers in every row has to be exactly the same. Here, there is an analogous sort of vectorial quantity that is conserved. So this is true. So there are two sort of vector winding numbers which I can rewrite in terms of its components. So there's fxx, fxy, fyx, fyy. So all of these are conserved quantities. So in 3D, I will add two more, right? So there will be some f, or not three more. So I have 6 of these in 2D. I have 4 of these in 2D. Two-dimensional vector quantities that are conserved in 2D. In 3D, I'll have three-dimensional vectors that are conserved. So one, again, interesting feature is these are all scale as the linear size of the system, not as they scale as L, not as L cube or L square, similarly to the spin problem. So that's where, and this is just for people, maybe for more nuanced or more a deeper discussion. That's where I think I have concerns about the definition of these intensive variables, because these things don't scale. The conserved quantities actually scale linearly with the system size. Not I can write down sigma, which does scale as the volume or the area, but the conserved quantities are slightly lower level or even deeper, right? So it's not that sigma is conserved. It's these, right? These vectorial things that are sort of conserved along different directions. So I don't quite know that's how that reflects into intensive variables. But setting that intensive variable question aside, using sigma to construct a coarse grained quantity is absolutely fine. Okay, so at this stage, I wanted to focus a little bit more on 2D and illustrate what these vectors look like. So I will just bring in a picture and then we can talk about this. So this is actually constructed, and this is a way of introducing the heights also. Okay, so I'm going to expand on this picture, and sorry if my notation changed. So what you're seeing here as gamma xy, gamma yx, gamma x yx, and gamma yy are what I call the f's. Okay, so what have I done here? So I'm going to illustrate. So this is in 2D, and the first thing to notice, what I wanted to show is that these sort of winding numbers, which are vectors, emerge very naturally in these kinds of particulate systems if I go through the definition of the analog of the height variables in the spin problems. There's a question in the chat. Very good question. Do we have to construct an analog of the dual lattice in the granular? Yes. So that's a very, very good question. And the dual here is the void space. So I can look at grain centers or void centers. And the heights actually sit on the centers of voids here, which is, so there's a no dual lattice, but there is a dual space. And so let me try and illustrate that through the definition of these heights. So what I'm showing you here, though, is an actual construction from a paper that we use this height representation to look at these suspensions that I talked about in the first lecture. So this is actually a suspension configuration, and the colors here are sort of the standard coloring of how strong the forces are. Okay, but this is what you see in the background, the blue and if I keep blowing this up, in the background here, you should be able to see voids and particles and void spaces, and this is a bidispersed system. So there are grains of two different sizes. The grains are actually the white circles, right? And then the blue parts of those are where the fluids are. So this is not dry grains, it's fluids. So you take such a system, and this is a blow up of this region, and now you can see, right, there are grains which are numbered, but forget about the numbers. So there are grains and voids, right? So these spaces are the voids, these are the grains. Now I can define, because just using force balance, and in 2D, I can define should have drawn these so they are going to be really messy drawings for me, but because I'm drawing them now. Okay, so don't focus too much on the accuracy of my drawing, but what I can do is the following. So these are contacts. And let's just look at the center grain. And I know that the forces on that grain have to add up to 0. So what I can do is introduce a vector sitting at these voids. And where they sit on the voids is I'm not going to get into that. There is a precise way of saying where they sit, and I can answer that later on. So I'm going to introduce a vector field, and I'm going to choose this void to to be the place where I choose the origin of this field. It's turns out to be a gauge potential, so the origin is where I choose the origin is irrelevant. But now I have the following rule. So the rule is, as I cross this contact, then I am going to at this point, I have a vector sitting at this void, which is going to be the contact force that I crossed, going clockwise, anti-clockwise around this grain. So I'm going in this direction. So you always have to sort of come up with a convention. So I'm going in that direction, and the direction of the force is the direction of the force exerted by this grain on that grain. So this contact force, if it was purely normal, would be pointing in that direction. So the convention is this contact force is the one exerted by the neighbors on the grain that I'm going around. Right? So now I can keep doing this. When I go to this grain, I have another HV prime, which is going to be, so let's say this was the first contact that I crossed. Right? And then I keep doing it, and then I come back to this point, and because, so I come back to my original V naught, that void, and that is going to be sum of C1 plus C2. In this case, I have only 4 contacts, and I know that to be 0. Right? So I can define this height, and you can convince yourself that because of the force balance on every contact, I can take any loop and come back, and it's a one-to-one mapping. Right? So as long as I follow the convention. So that's the definition of these are now these vector fields which sit on the disordered configuration at voids, right? So I have now, if you tell me how many voids I have or I have a set of height fields sitting on in the void space.
Bulbul, this I guess only works in 2 dimensions, right? 3 dimensions.
This only works in 2D. That's what I'm trying to say. So yeah, and you'll see what the analogs are in 3D, but I don't know how to draw them or use them in any way. So in a coarse grained way, these can all be translated to 3D. Not this, but this is very particular to 2D.
Because in 3D, these void spaces need not be disconnected, no?
Exactly. Exactly. So here we are using the fact that that the voids and the grains sort of form a bipartite graph. So let me try and actually draw that. That's actually an interesting. Yeah, so I'm going to draw it on here. So one way to think about actually making all of these calculations much more rigorous, much better defined, is going back to this question that someone in the chat asked about lattices and duals. Instead of lattices and duals, I can construct a graph where, see what I'm doing? I'm connecting the contacts on a particular grain. And so this is not an ordered network, but it's a bipartite, it's a checkerboard network. So these are my grain polygons. And somewhere here, there is going to be another, I don't know, somewhere, right? So this is a grain, this is another grain polygon, and these red ones are the void polygons. So I partition in 2D, I can partition space into these grain polygons and void polygons, and then the heights sit at the center of the void polygons. In fact, you can actually think of the heights as sitting as vectors on what's going on these links, but let me not get into that. So that's another way of thinking about them. So yes, this is absolutely true only in 2D. This I can do only in 2D because I have this bipartite structure and the void, and yeah, the in 3D, right? What Sanjib is saying is in 3D, the void spaces are connected, they're multiply connected. So I don't know how to define things sitting on them in a particular way. So this it's not a disjointed structure. Okay, but the best way to think about, right? So what's going to happen? So I take a particular configuration like this shown on the right, right? I construct the height on sitting on the voids. I want to be able to visualize these heights. Remember, these are vectors, right? So what I'm doing is I'm taking this 2D space, which is the granular assembly, and then I'm constructing at every void another vector. So of course I can draw these vectors as vectors in this as a vector field on this granular configuration, but there's a nicer way of thinking about them geometrically, which also very clearly identifies these winding numbers, these invariant quantities. So how do we do that? So this is, in fact, a simpler construction which I'm going to illustrate here. So for each grain, right, I have a bunch of forces. So I can take, let's say I take this contact force, so I'm going to call this FC1, FC2, and remember these can have friction, so they don't have to be along the bonds. What I can do is just say, okay, I'm going to start with FC1 and align that along my x-axis. Then I'm going to add to it FC2. I'm just drawing this arbitrarily. So I'm just adding these vectors head to tail. So I get a closed polygon, right? Because my forces add up to 0. And I can keep doing this. So if there's now another grain that's connected to this grain, might have 6 contacts, I don't know what it is, but it's connected to this FC4. So let me draw this here. Right, so now I have another grain, this blue grain, which has 6 contacts in it, which I can also, so its FC4 actually will go in the other direction because of Newton's third law, but I can keep drawing this and it will connect because of Newton's third law. So what I end up getting, if I keep doing this, is a picture like this one, right? So here is the granular, here is the grain picture, and here is what we call a force tiling, which also we can do only in 2D. And each grain here maps onto a polygon. So now I've sort of lost all of the real space information, where these grains were sitting in real space. I've gone on to an alternative, into a map where I'm only carrying the force information. So in these tiles, right, the force is are, if I'm going on this grain, the forces are pointing in this direction. If I'm going around this grain, the forces are going to be pointing in that direction because of Newton's third law. And now you can see that if I started from one point as the origin, like, so I call this the origin of the height field, then these vertices are nothing but the heights. So I construct this tiling, which I'm showing you on the right. I know that you guys can't see my pointing here. So this is an actual construction, right, from this. So this is a small part of here, which maps onto this tiling. And then if I keep doing it for the whole system, then I end up getting this tile with these boundaries. And these boundaries are these winding numbers. The two vectors. So there's a vector. These two vectors are what are the fx and the fy, or what I have called here maybe gamma y and gamma x. I keep switching notation, right? But so let me so I think I need to pause and sort of see where things, if I have confused people enough. But in 2 dimensions, what I'm trying to point out is there are these two sort of conserved vectors, and within them sit these height vectors, which are defined. I can define them in real space. I could have drawn vectors here, right? So these are some vector quantities. I could have constructed a vector field. To see this emergent winding number and how the heights are related in sort of a topological way. So from the 4 styles, I know what the heights are around grain 1, grain 2, grain 3, grain 4, even though I don't know exactly in real space where they're situated. So I don't have the information about the positions of the grains, but I have full information about the forces that are acting. So this is really a map that emphasizes the contact forces and the fact that they have to add up to 0. So let me actually pause for 5 minutes to see if, pause for a minute to see if there are questions.
So I'm confused with one thing. So if you're in your system on a torus, then isn't the total winding numbers will take only 0 values, or am I confused with that?
So I can no. So just like in the spin problem, right? Let's see if I have it here.
Yes, in the spin problem, they were
in this problem, right? In the periodic, my height. So for example, if all my dimers were parallel, my height would keep going up. And then I would get a discontinuity, right? And that's the winding number.
Yes, yes.
So the same thing here.
But here your winding numbers are forces in some way. Wouldn't that has to stress?
So if there are no external stresses, and this is precisely so. This now completely determined by what forces I exert on the boundaries.
Okay, so I got confused because you were saying you put it on a torus, and there I thought.
Well, it's a periodic. So so in the simulations, or they use periodic boundary conditions to shear the system. But of course, there are forces that are exerted not at the boundary, but there is a straining of the. They do Lees-Edwards and put shear on those. Yes, periodic boundary conditions, but with non-zero forces exerted somewhere. So what I mean by periodic boundary conditions, or what in this context a periodic boundary condition would mean, is that, I'm repeating this periodic system, but somewhere in this system I have actually exerted forces. So there is a non-zero pressure and a non-zero shear stress on the system that's exerted from the outside.
So that's your macroscopic like control, which is related
exactly.
to number.
Yeah. Exactly. So my macroscopic control.
So that's why you were saying that these could be the intensive variable. Is that why? But
I don't know if they're so just like in the spin problem, right? If I impose a field, a magnetic field, it'll determine for me what the winding numbers are. Here, by imposing, and you're seeing the fact that this system is sheared because there is a non-zero. This angle is sort of the shear angle. If I had a perfectly isotropically compressed system, this would be, there would be some square force style. But the size, right? So it's a very, so the larger I make the pressure, it's really a weird translation, right? So the larger I make the pressure in the actual real system, I'll compress the grains more. My volume would decrease. Here, my force style will increase because it's actually measuring the force. The dimensions of the box are given by the imposed forces. And so the reason that, so the forces, right? So this diagonal is the long diagonal. So that means the forces are on average higher in that direction. So that's the compressed direction in the real system. And this is the, so this is the compressive direction, then this is the dilated direction. So you have a complete 90-degree rotation of the real space picture, and whatever looks like compression here looks like the dilation in this force tile picture.
Yeah. And when you look at your real force networks that you have in the top picture, the only thing that translates is the coordination number of these force.
Exactly.
And
exactly. Right. And this, so whenever we draw pictures like this on the right, I have colored them by some threshold. That's why they show up. But the force tile has no threshold.
Right.
The force tile representation captures the smallest forces and the largest forces. And you can so what we did in the suspensions using this framework is actually construct an ensemble using the Edwards idea. So I don't think I have time to go into that. I can say a little bit at the end. So we actually constructed a partition function for these suspensions using these as my degrees of freedom, and phenomenologically figuring out, is there a kind of an interaction between the height vectors? Like we computed the pair correlation function of the heights, right, which I can do from these kinds of patterns. And then you can say, oh, let me use the sort of usual StatMech idea that I have a pair potential which goes as, which way am I saying it? Sorry. Let me say G2 is actually some, the low density approximations that we usually make, that this is some potential, some effective potential. There's no potential here, all right? It's just saying the pattern of these heights captured as a pair correlation function can be, let's assume, or I have defined V as the log of this. Then let's do an usual StatMech with this, and that actually captured the whole shear thickening phenomena in these suspensions. Because what happens is these patterns change dramatically as you go through this shear thickening transition. But it's again one of these ad hoc theories that we constructed, but based on this idea. And the reason that looking at it this way is more fruitful than looking at the positions of the grains is, as I was saying, the position, a small change in the positions of the grains can change the contact forces dramatically. So unless you know precisely how these grains are touching what, and in the simulations it's controlled, like it's, it's saying, oh, there's some rule saying when they touch, I have this tangential force. Even there, if you just look at the positions, there is nothing that you see in the positional correlations. Nothing happens. But if you look at the forces, dramatic things happen, just because it's this sort of scale separation that these particles are reasonably rigid. So just a small change in their positions creates large changes in the forces. And so it's just an effect, it's a way of looking at the system that's more productive than looking at positional correlations. Okay, I was going to stop in half an hour. So other questions from students? Other
Bulbul,
students? Yes. Yeah.
There's a question from Shubro who's watching this on YouTube. So yeah, so his question is, does the force styling fix the grain configurations uniquely?
No. No, it doesn't. No, it doesn't. Yeah, I cannot go back. Okay, sorry, modulo, if this was frictionless, yes, right, because then the forces are along the directions of the vectors. If they're frictionless and I knew the force law, then of course I could do the inversion. But not otherwise. But so these force tiles are known as Maxwell-Cremona tiles in the engineering literature. And there are some very interesting reciprocal relations for frictionless systems. So if the edges of the force tiles, right, these edges are actually along the contact vectors, which is true for frictionless, then there are exact reciprocal relations that one can work out. And for example, zero modes or floppy modes in the force tiles turn out to be what tell you what are the what stresses can be supported in the actual real space network. So I can actually look at the displacements of these vertices here and ask, do they generate, are these modes, like I can compute the dynamical matrix of this, the force tiling lattice and the dynamical matrix for spring-like systems, this reciprocal tiling, and has been used to, says my internet connection is unstable. Did I cut out or was it okay?
No, we can hear you.
Okay. So yeah, so there are lots of special properties when systems are frictionless, which can be utilized to get lots more information. So that was a long answer to Shubro's short question. Other questions?
I have one more. So in the spin cases, you had all these, the winding numbers were preserved by all these local moves. So here I'm a bit confused. What are the local moves which preserves the old stress?
Yeah, so here again, right? So if we go precisely what you asked earlier, these boundaries, right, of my force tiles are being determined by the external pressures or the external forces. That so unless I change those, I am not going to be able to change the shape. So I can move around these contact forces, but I cannot, let's say, change the sum of the contact forces from this boundary to that boundary.
So the question was that, so in the case of spin system, you could, given a fixed winding number, you could move from, there are many.
Right. So what are those moves here? So those moves for hard spheres are very difficult to figure out in a jammed system. But for soft spheres, right, they will be small rearrangements in the contacts, but the grains are not moving away from the position. So local moves are one is that the geometry doesn't change at all, right? You have very small changes in the contacts, and the forces change.
You mean you can change length of each forces, keeping the adjacency same and all the outside? Okay.
Yes. So the topology of the network doesn't change at all at any scale.
Okay. Okay.
Yeah.
Hi. Can I ask one more question?
Hi, Shubhra.
So maybe Trideep asked this question, but is it possible to sort of keep intact the force styling but change the configurations slightly?
Yeah.
Yes. So at no point, if I look at the force styling, it remains, say, if I think about a parameterization T from 0 to 1, so between two configurations, so I can continuously change the configurations, but the force styling remains static. Is it possible? I cannot figure out.
If I know precisely what the relationship is, so you're asking the reverse question. You're asking, can I change the grain positions and keep all the forces exactly the same?
Yeah.
Yeah.
For a few grains, it looks not possible, but I cannot figure it. Yeah.
Yes, I think that's so. The only to keep the forces exactly the same and change the and move the grains around. Locally, I don't think I can do that, but I think I can imagine. Yes, right. I can imagine. The reason I was saying it's not invertible, right, is I don't know how to go from the forces to the positions. But I think what you're asking is, can I keep the forces exactly the same and move the grains around? I don't think that's possible.
Okay. Okay.
Yeah.
So it is a many-to-one mapping, but once you are given one configuration, if you want to change the configuration, you must change the force styling.
Exactly. Yeah. Yep. That's correct. Other questions?
Ma'am, in the figure, gamma x and gamma y is like fxx and fyy.
Yeah, I think that's correct. I might have, it might be that what I call gamma y here is actually what I define as fx. I don't remember which way I did it here. It's possible, but but that's, yeah, at the worst, that's what it is.
So, like, can you just explain why? I mean, this part. I mean, I understand this force styling. From there, what is the conclusion? I didn't get it. Can you just explain what is this Kaju Katli shape? Which
is the Kaju Katli shape? Yes, that's a very good description of this. So if I just started from the four styles, forget about the way I started by defining these quote unquote winding numbers, right? What you see is that the four styles fit inside a parallelogram, right? Which has this Kaju Katli shape. Yeah. So the question is, so this is what determines in the shape or size of this large four styling box within which all my four styles have to fit, and that's defined by the stresses external stresses I impose on the system. And so what you see is, and so for an infinite system, here, if I blow it up, you might see, this is periodic boundary conditions. So if I had a finite system, then sometimes the four styles edges will actually come out of this parallelogram boundary just because it's a small size fluctuation problem. But then I go to the infinite system size and they fit inside. I don't know if that answered your question.
But the way f of x was defined was integral over sigma.
Oh, yes. Yeah. Okay. That connection. Okay. I can give you that connection. Okay. So what you're asking, so we'll probably not get to the tensor theory today, but that's okay. What you're asking is what's the relationship between these H fields and the stress tensor, correct? Because I defined the fx and fy that way. So yes, so the sigma tensor, which is the macroscopic tensor, the extensive quantity, there's this, so this goes as L. Yeah. Want the connection to the fields. Okay, so where did the fields come? Where do these height fields come from? It comes from the divergence of the stress tensor being 0. So the stress tensor in 2D can be written as a contraction of the antisymmetric tensor with this tensor. So it's the curl. It's the general definition of a curl. So if I write it this way, if I haven't done, let's just do it because I always mess it up. Right, so that's this tensor, and then I'm multiplying it by the completely antisymmetric tensor, so it's going to be so that's this tensor multiplied by an L, because this was the okay, let's forget the L. It's either L or L. Yeah, it's yeah. Okay, multiplied by something that makes it extensive. Okay, so that's the relationship between, so if I actually wrote the stress tensor, then it's just that. So now you see that this integral that I wrote down, let me just get it out from here. Where did I write it? Then this is an integral, right? So sigma xy is, so what I'm doing is integrating these two, this vector, correct? Oh, and that's why my definition is wrong. I should really have done this properly. So what it should be is actually integrating my fx and fy definitions. Ah, I did do it wrong. It should be integrating let me see. I did write it down last night, so it's probably here. Yeah, I have to write it this way. So then I do sigma xx, sigma xy, sigma yx, sigma yy. Yeah. Okay. It's just a this convention I did wrong. So this should be this might be the Fy, and this is what I was saying. So, okay, so I messed up a little bit, but not too badly. So this should be sigma xx, sigma xy, and this should be sigma yx, sigma yy, dy. Okay, so now you see what these are. Sorry if I'm confusing you guys again. So if I define it this way, and then I put in the del y, del x's, right? So then Fy is the integral of dx. It should be this integral of dy. Del y hx, del y hy. Okay, let's just look at that one. Does that make sense? dy minus L over 2 to L over 2. That's the definition of Fy. That's the winding number. So now you see it's just the difference in hx and hy across the boundary.
Yes, I get it. Yeah.
Right? So this winding numbers, and that's why they define the boundaries of the force time.
All right. Yeah. Thanks.
Right? So I go along this direction, I see a difference in the height vector. I go along the y direction, I see a difference in the height vector. And those are the two vectors. Sorry, I messed up the definition. I always do this. Okay, I think I'm going to skip talking about the tensor gauge theory completely. Let me just just introduce you to the concept, and because then it's too much otherwise. So, okay, so I'm just going to show you two pictures, and then we can talk about it more if we. So using this sort of coarse-grained continuum theory, what we were trying to understand are stress transmission in granular systems. So actually in dry grains for now. So if you impose certain stresses on the boundaries, or if you have gravity, then how do stresses get transmitted? And what we were able to show is that if you think of the forces as vectors in a kind of generalized electromagnetism, then there is a completely consistent theory of the stress response of the system. So I'm going to just, what I'm going to do is give you a mapping and then write down so that's all I think I have time to do. So there existed in the literature an electromagnetism involving tensor electric and magnetic fields and vector charges. And so at the end of the day, we were able to map that theory onto the dielectric version of that theory to the elasticity of granular materials problem. So the mappings are given here. So the stress tensor becomes the displacement field so that in a dielectric you have a displacement field and an electric field. The stress tensor becomes that displacement field. The forces become the charges. The bound charges are like there are dipoles that are created inside. So the bound charges are like the contact forces, because those are not net charges, right? So because of Newton's second law, they're actually dipoles. There are two forces that are equal and opposite sitting at some distance from each other, where that distance is pretty tiny. It's sort of the compression, or where the forces are exerted. So that's the mapping. And then we extended the theory maybe a little bit to the dielectrics, but other than that, the theory existed for us. So I'm just going to write down this vector charge theory Maxwell equations. In vacuum. I'm not writing even down the ones in the dielectric, or actually I can do that. Let me just do it in vacuum. So this, and I want to just point out the conservation laws that are in this theory, and maybe a couple more things. There's also a magnetic field, which has some magnetic charges in it. And then this, we get the negative, this is the negative, plus maybe there's some current. And then there's an Ampere's law. So it's sort of the exact analog of Maxwell's equations in usual E&M, but generalized to this vectorial charges and symmetric fields. So Eij is equal to Eji. Bij is equal to Bji. The electrostatics of this theory in a dielectric gives us a framework for granular, quote unquote, elasticity. And the reason this is very exciting and interesting is it never relies on a concept of strain. And the concept of strain is problematic for amorphous systems because I don't have no unique reference structure, unlike a crystal. And the reason that's problematic, if I just want to expand that on that a little bit, let's say I take a system and I strain it, right? So I'm going to, this is the usual sort of rheology or stress strain measurement that someone would do. So I have strained the boundary. And then whether there's a shear modulus or not, I will define the shear modulus by asking how much did the stress change with this strain, right? That's how I would define a shear modulus. My claim is that doesn't make any sense for an amorphous system. And the reason is the following. So when I do this, I have changed the boundaries. So I have introduced some displacements to the system inside. Now, if I have a crystal, if I have a completely ordered network, then whatever, and this is preferred because of some, right? So the displacements cost energy or free energy. Then as I strain it, the information that I have actually distorted the reference here translates inside because it's the same reference structure, right? So in a crystal, I start from this point and I know if I go a certain distance in this direction and a certain distance in that direction, I'll find another point there, another atom or a molecule. So the reference structure is given. Now, if I have a completely disordered system, then what I do to the boundary does not translate inside in terms of displacements. The displacements actually don't mean anything because the displacements are not about a reference structure. So elasticity emerges from broken symmetry. That's what we have taught. And the broken symmetry means there is a reference structure or there is a preferred structure. Now, in these amorphous granular systems, there is nothing like that. So the really satisfying result that came out of our exploration of this gauge theory is that you get something that looks exactly like elasticity theory, but there is no strain involved here. So that needed the definition of the dielectric. So ultimately what we end up with from this tensor gauge theory is that there is a del I sigma I j, which is equal to the forces that are the body forces or the external forces that I put on a grain. So if there's no gravity, this would be 0. So this is the analog. Sigma is the analog of the displacement field in the electricity theory. Which will be F body plus whatever F contacts I have. And I think we did write that in this. Maybe not, but here. So it's the total force, which is the external force or the body force plus contact forces. This map, so then, as in normal electricity theory, it's the E field, this E field that's conjugate or dual to the B field. And Faraday's law tells me in statics, using the one that I wrote down, because it's static, this is what is 0, right? So I have two equations then, that this is 0 and del I sigma ij is whatever my external forces are. And if we assume, just like in a linear dielectric, that there's some polarizability tensor that relates these two, then this plays the role of the elastic modulus tensor. And this equation, this double curl, this equation is actually satisfied by the strain tensor, which sometimes we don't think about, but that's, so this so the E fields map to the strain tensor. Sorry, I shouldn't use gamma. Let me just write strain. So the big difference is the following, and I'm going to end there. So in normal elasticity theory, we define a strain tensor, gamma ij, which is defined in terms of displacements from a reference structure. So the displacement vectors are tell me that I have changed the positions of my grains from their equilibrium preferred positions R naught. And what I'm saying is that that's no longer a valid concept because I don't have a unique reference structure. But this EIJ, the electric field in our gauge theory, can be written in a very similar form, where this phi is a gauge potential. it has no physical meaning. It's a gauge potential, which is very, very appealing because it says that the whole structure of elasticity theory can emerges in an amorphous system, which is obeying because of the constraints of force and torque balance and the global constraints. But what is different from normal elasticity theory is what were physical fields there, because I actually had a broken symmetry state. Here are just gauge potentials. Those are not physical variables anymore. But I still have physical observables in the E's and the sigmas and the B's. But there's no physically observable displacement field. And then the elastic moduli tensor are then a reflection of how polarizable this system is. So if I put stresses on the boundary and there are very few grains that are touching, then I cannot polarize it very much because there are very few contacts that will develop, or if the density is very low. But if I have lots and lots of grains, then it's very polarizable. And so so we don't have a theory, we don't have a microscopic theory for the elastic modulus tensor. So far, we have it as just coupling constants in this theory, but we have tested that it works. And I'm going to end there. I was going to end half an hour early. Now I have left only 5 minutes. So let me just stop. I'm now going to stop talking and see if people have questions.
Bulbul, I mean, can you briefly comment on what, as I mean, like from the point of experiment, like what kind of insights on this theory? Like you showed some experimental data. Like, can you just explain?
Yeah. So what I'll do is I have a talk on this that I'll post on the website, which shows the slides, the data, etc. But roughly speaking, let me tell you one thing. Let me see if I stop sharing here. Actually, no, I have it here too. Yeah, you can see these, right? So, okay. So just as in sort of any other field theory, the main thing that we want, the thing that we can compute are correlation functions, right? So what we can compute are the stress-stress correlations. So what I'm showing you here are, and now stress-stress correlations I can do between sigma xx, sigma xx, sigma x, so the many of these, right? So the real remarkable property, the success of this theory was we could take all of these correlation functions that were measured experimentally in one of these photoelastic experiments where they could actually construct the stress tensor and describe it by the theory. So what you're seeing here are the black lines are the theoretical predictions and the dots are the experiments. And what you're seeing, what is really remarkable about a universal property of the stress-stress correlations, because of the divergence-free nature and the vector charge, are these appearance of these pinch point singularities. So if I approach the 0Q, this is all in Q space, in different directions, I get different results. So there's this. So these pinch point singularities, which are sort of quadrupolar in nature, are the sort of hallmarks. And what I'm showing you here is that by adjusting essentially one number, which is the overall value of lambda, we can describe the experiments.
So this experiment is like with it's a 2D.
It's a 2D photoelastic beads. This is with isotropic compression, and then we also looked at a sheared system. So for the sheared system, this lambda tensor becomes anisotropic. There are different components, so we needed two to and even those so there are some ways we can understand the basic properties of this. One thing that I want to point out is the following. So we talk about force chains, right? So what these guys, these experimentalists had done even before we had the tensor gauge theory is to say, what do these force chains mean? And what they ended up doing was coloring. So if you take a look at this picture, it's the same configuration in this, and that. In this picture, they have colored the grains by the magnitude of the XX component of the stress. In this picture, they have colored it by the magnitude of the YY component of the stress. And in this, they have colored it by the XY component of the stress. So what they were pointing out is what really force chains are telling me that if I am looking at grains colored by sigma XX, then they propagate along very long directions in the X axis, but they die out along the Y axis. And that's a property of these correlation functions. So the longitudinal and the transverse component. So if I look at sigma XX, sorry, now I have to write here. Let's see, should be able to write. So if I look at sigma XX along the X direction, they all decay as power loss. There's no length scale in these. These are really like Coulomb phases. So it goes as R, 1 over R in 2D. If I look at, this is along the X direction. If I look along the Y direction, they actually very quickly become negative. And that's just a consequence of the divergence-free, what the divergence-free condition imposes on the stress-stress correlations. So so if I now color by YY, looks like the chains are in the Y direction and not in the X direction. So it's just this longitudinal versus transverse correlations. And that's connected to this idea that forces are vectors. So if I have a force, if I put a force in that direction, it primarily propagates along this direction. If I put a force along this direction, it primarily propagates along that direction. So this is this sort of subdimensional propagation of charges that people talk about in the spin system and talk about fractons. So one remark, and then I'll stop, is these these correlations showing the pinch point singularity, which are a hallmark of these vector charge theories. People have been looking for them in quantum spin systems and have not been able to find. And we, in this very macroscopic system, see this by measuring stress-stress correlations. So this is, in some ways, it's saying maybe we can learn something from these systems to go back to the more microscopic systems. But yeah, so I will post these. I have a set of slides which shows all of these results, and people can even ask me next week if you want to think about it.
Yeah, any other questions?
Yeah,
Yes.
I have this feeling that I have lost most of the students, so I'm
Yeah, so are there anything that you could say related to the jamming transition and scalings around it?
Yeah, so that's the caveat. We very carefully stayed away from the jamming transition in looking at these. So these are sort of in the deeply jammed region.
Right.
And then what we have realized is that this comes back to this coarse graining length scale. So we want to be able to define to define this electrostatics, I need to be able to coarse grain over a length scale where I don't necessarily create magnetic charges whenever I create electric charges. And because the magnetic charges are actually related to the momentum density. So, and that region scales as a length, the smallest region over which I can do this scales as 1 over z minus z isostatic to some power. So that says as the closer I get to the unjamming transition, the larger my coarse graining box size has to be. So basically it's saying that the gauge theory or the coarse grain description actually collapses at the, I don't have that. I cannot construct this sort of clean separation between electric charges and magnetic charges and electric fields and magnetic fields at the jamming transition. So in some way, this whole theory is falling apart.
But that is exactly sitting at the transition. But if you, is there some distance?
So, right. So if I'm at some, so we've gone reasonably close to that transition in the simulations. And we haven't actually changed our coarse graining size very much. So it works reasonably, but it's really so when we say we're getting close to the jamming transition, the pressure, right, the imposed pressure at that point goes to 0. So even a pressure of 10 to the minus 5 is actually quite far away from the jamming transition. So we haven't explored exactly how it falls apart as you get very close to the unjamming transition, right? So we are always coming from the jammed side and seeing how it falls apart.
Okay.
Bulbul, I had this question. So you had this, from this brain, you had this force tiling diagram, right?
Right.
Yeah, you said it's in 2D. So in 3D, why can't you do that? It will not be tiled, but is there not unique configuration in terms of this force thing?
I actually, so there is actually, so the height is the potential, right? That solves the Gauss's law for me in 2D. So in 3D, that's a tensor. So the field becomes a tensor. I don't know how. So that we know right now, right? Or we have known for a while. And we can write down coarse-grained theories for what these fields should be doing. But how to geometrically construct that tensor is something that's not clear to me. So let me see if I can. So let me just say, since Sanjib asked this, so the Gauss's law, if I want to solve, I'm just using the E field here, is equal to 0. Then and I'm now using sort of the dual. I'm solving the Gauss's law. Then Eij or sigma ij. Let me just say sigma ij in 2D. And the psi is related to the height field in that H is curl of psi. And this is the point I have sort of shoved under the rug today, is I need this to satisfy torque balance. So really the underlying potential in 2D is a pseudoscalar. In 3D, I have the full thing. So the potential is a tensor itself. So I don't know how to construct it microscopically. Actually, even this is problematic to construct microscopically in 2D. The height fields are very easy to construct, but a discrete representation of psi is a little bit complicated. I'm going to stop sharing so that maybe everyone can show their faces, because I haven't seen.
Yeah. Yeah, maybe people can unmount.
Yeah. Can people just, I find that when I'm teaching also. Yeah.
Right, yeah. Okay, so or you can at least use your reactions to thank Bulbul for really wonderful set of lectures, and we hope that we'll have her at ICTS sometime soon. I don't know when.
So too.
Yeah, that's much better.
Hi, Jatin. So I'm also saying that if people want to email me next week with questions, I'm happy to answer.
Yeah, okay. Yeah, so
okay.
Yeah, so thanks again, Bulbul, and yeah.
No, thank you.
To see
Yeah,
you
this was. I wish this was in person, but yes.
Yeah, it's right. Yeah, there's nothing like in person meeting.
Yeah.
Yeah, thank you very much, Bulbul.
Someone said something.
Thank you.
Okay. Thank you. Take care.